Okay, so I'm back. Hi guys. So as promised, I'm gonna do a short video on Hess's law and enthalpy change. These were already discussed during our sync classes, but I'm just compressing them now so that they will be easy to view videos that you can go back and review once you need them. Okay, so let's go back to Hess's law. So as defined, here we go again. So as defined. So it says here that Hess's law, or most often it's also called it's the law of constant heat summation. It states that regardless of the multiple stages or steps of a reaction, the total enthalpy change for the reaction is the sum of all changes. This law is a manifestation that enthalpy is a state function, meaning it's an independent function that even if we break down reactions into smaller sub-reactions, the heat total or the summation of the heat will be the same. So there's a little diagram that will show that. So here you can see from this that no matter if you take one route to get to the product or another route to get to the product, even if you divide the reactant into sub-reactants, the product, which is of course enthalpy. We're talking about enthalpy here. So just isolate the ideas into in enthalpy. So the total heat will be the same. So meaning it's just really summation. All you have to do is understand the reactions, how they are, and then to get the total heat reaction, it's just the summation. Okay, so let's go to an example. I believe that these are the important ones that you need the review on, or you need the guidance on, since in the same class, this were mostly where we were really interactive. So I have three examples in this video. So I'll start with the basic one, not basic, not meaning basic solution. I'll start with an easy one, going to a more complex examples for the last two problems. Okay, so this one, it simply says find the total energy change for this process. We're breaking down water to two hydrogen and two oxygen, and also we're breaking O2 to that 2O. Okay, so what do we do? So this, by the way, if you're wondering where we get these are actually heat. These are um, these are the heat constants or delta H. There's actually a table, or there are tables on your books online that you can refer to. Maybe on a separate video, I'm gonna guide you on how to use the tables. But for this video alone, the heat of enthalpies will be given. So we're just trying to combine these two reactions to get this final reaction. Okay. So as I've said during say classes, the technique would be to understand the positions of the elements where they are. Are they on the left side of the arrow, or are they on the right side of the arrow? And that's where you start your observation or your inspection. It's not really called an inspection method, but on my end, that would help you a lot to understand the placement of the elements in the reaction. So here we have 2H2O yielding 2H2 plus O2. Looking at that, so probably uh, it's not really trial and error. You can actually go to the next second reaction and then go to the other one. It depends on how you would analyze it, because as I've said, Hess's law is a state function. It's an independent function. So no matter what order you follow, if you're doing your process right, and if you're doing your analysis correctly, then we will get the same answer. So here, the position of water is on the left side. But for the product, the position is in the right side. So what we can do is we can use this and inverse the reaction. So by inversing it, and by the way, you can also see that on the product, it's only one H2O, and this is already two H2Os. So what do? We will divide it by two, the whole reaction, and then inverse the reactant and the product. So I'm doing that now. So let's call this equation 1. And let's call this equation 2. So let's invert the positions. So that will be n divided by 2. So that's H2 plus O2 over 2 yields what? H2O. Okay? I already divided this into 2 because my yield here needs only one water on the right side. And what did I do? I actually inverted uh, the positions. So it means that I'm going to expect something negative here for the enthalpy heat. Okay, for that heat. Plus, since I divided it by 2, I also have to divide it by 2. So it's 576 divided by 2. So we have a negative 288 kilojoules. Okay. Now for the second reaction, let's check. Look at it. For the second reaction, we have O2 yielding 2O. It's actually balanced. So, but O also needs to be on the other side. And it's also just one O. So let's do the same thing we did with the other one. So that would be O only yielding O2 over 2. And also let's do a negative here because we inverted the positions and then divide 495 divided by 2. So that's actually 247.5 kilojoules. And then I think we have it already. You can actually cancel. You know how to do this already because when we had our redox, you were already canceling elements from the product and the reactants. You know that if it's in both, it's in either side of the arrow, so you can actually cancel them. So this is O2. I can cancel that out. And there you go. No more elements to cancel. So what do we do? So that's just H2 plus O yields H2O. There you go. It's a check. And what happens? All you have to do is add them because that's really Hess as well. Just add or as a just a summation of the heat that were involved in the reaction. So 288 plus 247.5. So we're getting 535, but that's also a negative 0.5 kJ. So if you want your final answer, that is your final answer. Okay? So if at this point you have questions, please don't forget to jot them down and just route them over our Canvas, our messenger chats, or our FB group. Or you can message me on my Canvas inbox. Okay? So I'm by the way, I'm gonna put discussion board so that you can put your questions there. After each video, I'm gonna do them in a discussion board style so that you can actually just jot your question, and then if some of your classmates would have the answers already, and then they might just put the answers there. Okay, let's have another example. Okay, let's increase the difficulty a notch. So this is a three reaction process yielding this. So our target would be to get this. Okay, that's well, I'm not gonna read them. All we have to do is understand what positions they will be getting. So another rule of thumb that I was following when I'm solving such problems would be look for an element or a compound that is unique, meaning I don't see it in other reactions like here, like NO. I have to leave it here because NO, I can't see any NO on the other two reactions. So I'm just gonna leave it so that equation, it's gonna stay put. Okay, let me see if I have, yeah, I have a blank. Okay, let's see if no, I cannot copy that. So I hope you don't mind. I'm gonna take a picture so that I can copy them. I really don't have copies on my phone. I'm just gonna take a picture. There you go. Really showing off my phone. So let's write the given. And I think am I on my pointer tool? No, not yet. I removed the pen. Okay, so Let's rewrite them. I'm going to make it smaller so that's going to fit the screen. So that's 2O3 yielding 3O2. I have O2 yielding 2O. And then I have NO plus O3 yielding NO2 plus O2. And for the heat of enthalpy, we have 427, 495, and 199. That's 427, 495, and 199, right? Let's check that again. Yes, 427, 495, and 199. So the two are actually negative. So there we go. And then these are all in kilojoules. Okay, so what do we do? Well, as I've said, by the way, the end product is actually NO plus O, and that's an NO2. So the technique, again, as always, the technique is to check for the positions of the elements in the final product and then check your subreactions. And as I've said just a few moments ago, look for an element that is unique. Okay, so in this case, NO is unique. So I think I'll just let it stay there. So let's rewrite that. I won't do any changes to NO. Okay, that's NO2 plus O2, and that's a negative 199 kJ. Okay, now we have O2 and we have O3. Okay, we need an O. Here we go. We need an O in the final output or in the final product. We can get the O here, but that's only one O. So what I can do is, of course, do the switch. It's going to be O yields O2 over 2. Since I change signs, so this is going to be a negative. And then, of course, 495 divided by 2. Okay, that's 495 again divided by 2. This, of course, 247.5. Really using my calculator to avoid any mistake. Okay, why I arrived at that? Why is it negative first? It's negative because I switched it. I switched the places of O2 and 2O. And then since I only need an O in this part, I'm dividing that 2O into 2, meaning I have to divide the whole thing by 2. Okay, that's O, O2, and then of course, changing the signs and dividing it by 2. And then finally, what about um what about 2O3 and 3O2? Okay, we really don't need an O3 anywhere. So what we can do is cancel that O3. And where can I cancel that? I can cancel that here. So I need to leave an O3 on the right side. So I'm going to switch that as well. So switching that, so that's divided by 2. Okay, let's see that. That's O3. And then this becomes 3O2 divided by 2. And then I'm also going to switch this and then divide it by 2. So that's 427 divided by 2. That's a 213.5 kJ. And it's positive because I switch the positions of O3 and 3O2 and then divide the whole thing by 2. Dividing this by 2 just gives you O3, and then dividing this 3O2 over 2, that's it. So that becomes positive, and then 427 divided by 2. Then finally, let's check if we can really cancel them out. So this is 3 over 2, meaning that's 1.5. So I can cancel that. That's 1.5. Do we have another 1.5? So here you go. 1 and then 0.5. And then what about O3? Yes, you can do that. And finally, your final answer. Our answer is actually NO plus O yields NO2. And then for the heat, the total heat is, okay, that's 199. So our answer is actually negative 233 kJ. Okay. Hopefully, at this point, your understanding is increasing. I'll still solve one more after this. Okay. You can always pause it and then go back to it for parts of the solution that you might need clarification on. And of course, you can always ask me questions later on. Okay. I'm doing another one. So this is the third example. There, it's smaller. I tried to edit it, so I'm getting something smaller here. So I hope you can see it clearly. So this is the reaction, and then our final reaction will be this one. So also we're looking for total energy change given the following heat. So let's just check. Again, look for something unique. Well, on my end, what I'm seeing is this is the unique one, which is CH4. And I have to switch CH4 because CH4 is on the left side initially, but on the product side, it needs to be on the right side. So I'm switching that. So I'm putting CH4. Let me do that. So CH4 yields C plus 2H2. And since I switched the places, the heat, wait, what did I do? I think I copied the end result. I have to erase it. Okay, let's erase that again. Oops. Okay, there you go. I'm doing that. I copied the end result. So let's do that again. I'm sorry for that. I won't redo the video. I'm just going to go ahead and do it all over. So again, I was looking at this, but I was writing this. Imagine that. So CH4, again, CH4 is on the right side. It has to be on the left side, or it's vice versa. That's why I think I missed that because I was going through this as a reference. So I have to do this as a reference. So, okay, enough. So that CO2 plus 2, H2O yields what? CH4 plus 2, O2. Okay, why is that? We need proper placement of CH4. CH4 is unique. That's why we started with the one with CH4. So the heat becomes positive. That's 212.8 kJ. Okay, what's next? We also need a C. So let's carry over this. We don't need to, switch. Just copy it as it is. That's C plus O2. That's CO2. So no changes here. That's 94.05 kJ. Okay, I have the elements of my final reaction except H2. Do I have H2? Not yet. I can see C already, but I don't see H2 anywhere here. So, but I can see H2 here. So do we need something to inverse it? I don't think so because H2 should stay on this side, on the left side. So, but it has to be 2. So what we need to do is actually just multiply the whole thing by 2. So that's 2H2 plus O2 yields 2H2O. And then we multiply 68.32 by 2. So that's 68.32 times 2. We're getting 136.64. Okay. Okay, let's just check them again. That's 68.32 times 2. Okay, that's 136.64. Okay, finally, last step. You're almost there. You're almost finished with the problem. So cancel what needs to be canceled out. So water. And then, is there anything else that we can cancel? O2, right? We don't have a final, on the final product, we don't have oxygen. So 1, 2, it's already 2. Okay, what else? CH4 stays there. But do we have a carbon dioxide on the final reaction? No. So we can cancel carbon dioxide. And I believe that's it. So our final answer is C plus 2H2 yields what? CH4. There, it's the same. Now for the heat, all you have to do is add them. So that's 212.8 minus 94.05 minus 136.64. We're getting negative 17.89 kilojoules. Okay, there you go. So those are, I believe, the three examples will be enough to guide you on your solutions to Hess's law, which you can use in both your Chem Eng and your Chem Eng lab. Okay, so for now, that'll be it. So if you have questions, please let me know. You can always message me on our messenger chat. You can also uh, comment on the video. It's uploaded in YouTube. All the videos that I'm posting or making are uploaded in a YouTube channel. Please feel free to subscribe, and you can also share them with your other batchmates taking the same subject. So for now, please wait. I have another one to be uploaded also anytime soon. So please always view our videos. If there are questions, don't forget to ask me and feel free to ask me. You can always comment on the comment box once this is uploaded so I don't miss your comments and your questions. Okay, for now, that'll be it. Thank you for watching, and hopefully you understood the lesson about Hess's law. Okay, bye-bye.